sine wave, S-I-N-E, because it mimics the sine function, the trigonometric sine function. All sine waves are sine functions when graphed in amplitude versus time coordinates, as you see here. Time proceeds from left to right, past to future in any graph like this, and amplitude basically means signal strength, but for all intents and purposes here we can also refer to it as instantaneous voltage. Negative voltage is going down, positive voltage is going up. So for example, each time increment might be 1 second, and each vertical increment might be a volt, plus 1 volt, plus 2 volts, plus 3 volts. In that case, the period of the wave is the time it takes for one cycle to be completed. In this case, 6 seconds. 1, 2, 3, 4, 5, 6. You can see that. And the amplitude or voltage, if this is 1 volt per division, looks like about 2.2 volts plus peak and 2.2 volts minus peak. So that is the simplest possible wave in electricity and electronics, and ideally it would be what came out of your wall outlets, although that's not always true. The next type of wave I'd like to talk about is known as a square wave. Square meaning that it squares off at the corners, like this. What you will see if you look at a true square wave on an oscilloscope that shows voltage versus time is something like this that you see up here in the graph at A. The transitions occur so rapidly between the positive and the negative that you can't even see them in a true square wave on an oscilloscope, but you will often see it graphed like that. And another characteristic of a square wave is that the positive and the negative voltage flat tops here last for equal lengths of time, so that in this case, if we look at 1 second per division horizontally, then that lasts for a second at the positive voltage, that lasts for 1 second at the negative voltage, and the period, the time it takes to complete one cycle, is therefore 2 seconds, one complete iteration of the wave. That is known as a square wave, sometimes called a rectangular wave, although rectangular waves encompass a little bit more general type of wave where the positive and negative durations may not be the same. The next type of wave I'd like to talk about is known as a sawtooth, because it rises instantly and then decays at a steady rate. Rise, decay, rise, decay. And here again, if we consider 1 second increments on the horizontal axis, the time axis, then one cycle is this much. 2 seconds is the period of that wave. Again, we would normally think of amplitude in terms of positive and negative voltage. Time in terms of seconds, milliseconds, microseconds, nanoseconds, or even picoseconds. This is another form of sawtooth wave where it rises at a steady rate and then drops instantly. This type of wave is sometimes known as a ramp, R-A-M-P, because it's like a ramp going up with each cycle. And again, a full cycle, say starting here, it takes 2 seconds if we consider each horizontal increment as 1 second. Those are just arbitrary increments, by the way. They can be just about anything you want them to be. Same with the voltage. Now this particular type of wave is known as a triangular wave. It's not a true sawtooth. Sawtooth waves, actually, the ramp wave is a specialized form of sawtooth. These are sawtooth waves because they look kind of like the teeth of a cross-cut wood saw. But a triangular wave like this, it's referred to as triangular because of this shape like that. It has steady decay, steady increase, usually at the same slope. So here, one cycle, you would start here and come back to the same point on the wave. That would have a period, if we have 1 second per division, of 4 seconds. 1, 2, 3, 4. So those waves are the common waves you're likely to encounter, and combinations of those types of waves, any of those 5 types of waves, will give you just about any kind of wave you can imagine. An irregular wave like this. Theoretically, any wave can be broken down into an enormously complicated, or oftentimes enormously complicated, combination of sine waves with various amplitudes and various periods. Even my voice can be thought of that way, and to that end I would like to show you what my voice waveform looks like on a computer program known as Hamscope, which is in fact like an oscilloscope. Time on the horizontal axis, voltage or amplitude on the vertical axis. I'm talking more quietly here because it's very easy for me to overload this program with the way that my microphone is set. But even this complicated wave like that, even that complicated a wave, ultimately, in theory, can be broken down into sine waves like that.
Discussing about the square waves. So, what is a square wave? Basically, a square wave is a non-sinusoidal wave which changes its amplitude abruptly in between two fixed values. These values can vary from negative to positive within the range of supply voltage used in an electronic system. There are many ways by which we can generate a square wave. The generated wave can be called as a square wave if the signal is switching in between two different voltage levels with negligible transition time. The square waves are widely used in the digital circuits as a clock signal for synchronous application and also as a data signal to transmit data in the form of binary. Here, a logic high represents the binary data 1 and logic low represents the binary data 0. Before going too far, we need to know what are logic levels in digital circuits. So, a logic level is nothing but a specific voltage or a state in which a signal can exist. Usually, when it comes to digital circuits, we mainly use two different logic levels. TTL, which has voltage in the range of 0 to 5 volt, and CMOS, which has a voltage in the range of 0 to 3.3 volt. For example, if we consider TTL voltage level 0 to 5 volt, to represent logic 0, the voltage doesn't require to be exactly 0 voltage. It only has to be near 0 voltage. Usually, a device trying to send a logic 0 has to keep a voltage less than 0.4 volt. And to read 0, it has to be below 0.8 volt only. Similarly, there is a defined level for logic high also. Now you might have understand the square waves theoretically. But do you know where do we use these square waves in real world? Do you know how do we blink an LED in an electronic circuit? Do you know how do we switch a relay in an electronic circuit? Yes, for these kind of applications we use square waves. Similarly, do you know how do we transmit a data between different peripherals in embedded systems? Do you know what kind of signals are used in different protocols such as I2C and SPI? Since you understand the logic levels, now you can easily say that these signals are different variations of square waves. Square waves or its different variations are widely used in different digital circuits, embedded systems, and digital computers. I hope you understand the basics of square waves.